Displacement distribution of random oscillators. The displacement of a classical simple harmonic oscillator as a function of time is given by x is equal to a cosine omega t plus phi, where omega is the angular frequency of the oscillator, a its amplitude of the oscillation, and phi is an arbitrary constant which can have any value in the range, arbitrary, in the range 0 to 2 pi. Suppose that one contemplates an ensemble of such oscillators, all of which have the same frequency omega and amplitude, but they have random phase relationships, so that the probability that phi lies in the range between phi and d phi plus d phi is given simply by d phi over 2 pi. Find the probability that the displacement of an oscillator at any given time t is found to lie in the range between x and x plus dx. Now, the displacement as a function of time is given by a cosine omega t plus a phase phi. Now we are asking at any given time t, what is the probability distribution function for x? So a, omega, and t fixed. So we have basically x also a function of phi, which is a cosine omega t plus phi. Now, we already know that the phase can have any value in the range 0 to 2 pi, and it is an arbitrary constant in this range, 0 to 2 pi, in our ensemble of oscillators, so it can have any value with random phase relationships. So phi can have any value in the range 0 to 2 pi with no preference. That's the meaning of random. So therefore, if you consider the probability distribution function integrated from 0 to 2 pi, probability distribution function d phi, this should be equal to 1. And since there is no preference, probability distribution function should be a constant c for phi between 0 and 2 pi. And basically it's a periodic function, so I'm just assuming that it cannot have any other value. So then otherwise 0. So it has to be between 0 and 2 pi. That's what we are assuming. Actually, we're also excluding 2 pi here because 0 and 2 pi are the same thing because it's a periodic function. Okay, so c, this is going to be integral 0 to 2 pi c d phi equals to 1, which means c times phi between 0 and 2 pi equals to 1. C times 2 pi is 1, so c is 1 over 2 pi, so that, as suggested in the problem, probability distribution function for phi, p phi d phi, is d phi divided by 2 pi. So that is correct. Now I want to transform from phi to x. So in order to do that, I have to know the relationship between phi and x. So let's think about how many phi values correspond to the same x value. So this is a question we have to be careful with, because if you plot x as a function of phi, where phi is between 0 and 2 pi, okay, so this is going to be plotted between 0 and 2 pi, I will see it's a cosine function, so it's going to start out, well, it depends on the value of omega t and a. Omega t a fixed, and let's say that for phi is equal to 0, assume that this is going to correspond to x is equal to 0, so that I will have a cosine pi over 2, which is 0. So x is equal to 0. Let's assume this initial condition. Then I will have, as the angle increases, the cosine function is going to increase. So between phi equals 0 and phi equals pi, I'm going to have a positive cycle, and then I'm going to have a negative cycle, because it will behave like a sine function here. So this is basically phi between 0 and 2 pi. So this is phi equals to pi, where the cosine function would normally give you cosine pi is -1, but because I have this condition that when phi is equal to 0, I have x of phi is equal to 0 is a cosine omega t. This must be 0. That means omega t is fixed at pi over 2. So so my function is basically x of t that I'm plotting here is a cosine pi over 2 plus phi, so that when I have phi is equal to pi, that means I really have a cosine 3 pi over 2, and that is going to give me 0. Okay, and when phi is between 0 and pi over 2, I would have, for example, for phi, when phi is pi, I would have cosine pi, which is -1. So this actually cycle would look like this, instead of a positive cycle at the beginning. With this assumption, I would get a negative cycle first. Negative values first and then positive values. For example, taking pi over 2, I would get a cosine pi, which is -1. So pi over 2 would correspond to -1, etc. So what I want you to notice here, this is an oscillation between -a and +a. So if I fix the x value, so let's take this a particular x value, let's call it x naught, and look at how many phi values I have corresponding to this x value. You will see that I have one phi value here and another phi value here. So the mapping between x and phi is not 1-to-1. So for each x value, corresponds to, we have two phi values. The only there is only one exception here, that's the extremum points, but then you can say that the two phi values are the same for that point. Okay, so what is the probability of having a phi value in the range here to here and here to here. And since we have the probability distribution function giving me 1 over 2 pi, and it's independent of where it is, so it's the probability is the same. So because of this relationship, I can conclude that the probability distribution function of x, p of x dx, I have to consider two different phi values, but the probability distribution function for those values is the same, so it's going to be twice the probability of having a phi value in the range phi to phi plus d phi, because it's the same for the first phi value and second phi value. They're both 1 over 2 pi, so I just have to multiply it by 2 to find the answer to what is the probability of having an x value between x0 and x0 plus dx. Okay, so there is this factor of 2 here that I have to consider. Okay, so this is similar to, let me give you some more ideas here. So this is going to be, this is not related to this problem. If you remember the spin system where I had the net moment in the up direction, where m was defined as number of up spins minus number of down spins, for a total number of spins capital N, so n plus n prime was equal to capital N. So we had for n prime n minus capital N, so m was 2n minus n, and then here we had for every n value corresponds to a single m value for the spin system. So we said that probability of having an n value was the same thing as probability of having an m value. So this was for the discrete case, but we have a similar situation here, but instead we have for every x value two possible phi values. So we have to we cannot write this p of n equals p prime of m as p of x equals p prime of phi. Here we have the factor of 2. Okay, so now how do I go from x to phi? So x is equal to a cosine a multiplied by cosine omega t plus phi. So what is dx, where a, omega and t are fixed? It is the derivative of x, partial derivative with respect to phi, d phi. So what is the partial derivative with respect to phi? It is minus a sine omega t plus phi d phi. And since I want to write it in terms of x here, I also noticed that x square is equal to a square cosine square omega t plus phi. Therefore, if you write x square over a square, that is cosine square omega t plus phi, which is 1 minus sine square omega t plus phi. So I noticed that from this equation, instead of sine omega t plus phi, I can write the following: sine omega t plus phi can be written as square root of 1 minus x square over a square. Okay, so sine of omega t plus phi is going to be, here this can be plus or minus, by the way, as you can see here. So I'm going to decide on the sign at the end. So this is plus or minus square root a square minus x square over x square, or plus or minus 1 over a square root a square minus x square. So that's what I should consider here for sine omega t plus phi. Now I substitute this into dx, so dx is equal to minus a sine omega t plus phi plus or minus, which root I will take I will decide now, 1 over a square root a square minus x square. So this is going to be my for sine omega t plus phi. This is what I can write in terms of x. So therefore I see that dx is equal to minus a times sine omega t plus phi, which is plus or minus 1 over a square root a square minus x square d phi. So these a's will cancel, and I will take, so I want to have x in the range minus a to plus a for this oscillator, for the simple harmonic oscillator. Therefore, the quantity in the square root a square minus x square is going to be greater or equal to 0, which means for dx to be positive, I have to take the minus sign. Must be taken. For sine omega t plus or minus sine omega t plus phi, I will take the minus 1 over a root in order to get a positive dx value. So dx is going to be equal to square root a square minus x square d phi here. Okay, so probability distribution function of x dx is equal to twice the probability distribution function of phi d phi, and the probability distribution function of phi is not really a function of phi, it's the same for all angles. It is 1 over 2 pi, and for d phi I'm going to write dx divided by square root a square minus x square. These 2's will cancel, and therefore I will find that the probability distribution function x dx is 1 over pi a square minus x square to the power minus 1/2 dx. Okay, so let's go over this one more time. We're considering simple harmonic oscillators where the displacement is given as a function of time and phase as a cosine omega t plus phi. Normally this omega is a constant. We watch the oscillations in time. Now we have fixed the time, and we have an ensemble of these oscillators that have a random phase relationship. And so we would like to know, given that the angle phi can take any value between 0 and 2 pi with equal probability, what would be the probability distribution function of x dx for any given time t. So a, omega, and t are fixed. Phi is a random variable that takes values in the range 0 to 2 pi, and we would like to know the probability distribution of x. So as I have verified here, because the probability distribution function has to be normalized and it is a constant for every angle between 0 and 2 pi, that constant times d phi integrated over all possible values should give me 1. So that constant is 1 over 2 pi. So I have found that p of phi is equal to 1 over 2 pi. Now, how many phi values correspond to the same x value? Basically, I would like to know what is the relationship between probability distribution of phi and probability distribution of x. So I have fixed omega t and a. I have assumed that when phi is equal to 0, x is equal to 0. That means I have a cosine omega t is 0 at this time, so omega t should be equal to pi over 2, because cosine pi over 2 is 0. And from pi over 2 to, for positive phase angles, if I go above 0 and approach pi, I'm basically in the negative range for the cosine. So I would have, if you plot x as a function of phi here, I would have this type of an oscillation for phi values between 0 and 2 pi, between starting from negative values from minus a to plus a and going back to 0 at phi is equal to 2 pi. So I noticed that if I take a fixed x value here, there is a set of two phi values that correspond to the same x value. So if you have the probability of finding a phi value for two distinct values of phi, you will find that you have a single x value corresponding to it. So the relationship between probability distributions of x and phi is that probability distribution function x dx is twice the probability distribution function phi d phi. And why is it twice? Because the probability distribution function is a constant 1 over 2 pi. So for those two different phi values, even though I write it probability distribution function is a function of phi, it is actually a constant 1 over 2 pi. So it's not a function of phi. So I can just multiply it by 2 in order to get the answer for x. And since x is equal to a cosine omega t plus phi, and a, omega, and t are fixed, only phi is changing. The change in x dx is partial derivative of x with respect to phi d phi, which is minus a sine omega t phi plus phi d phi. And I can also write x squared is a squared cosine square omega t plus phi. I find that sine omega t plus phi can be written as plus or minus square root 1 minus x squared over a squared, because cosine squared plus sine squared is 1. Now, am I going to take the positive root or negative root? I decide here, because the dx I want to consider to be positive, and x has to be in the range minus a to plus a in the simple harmonic oscillator. So square root of a squared minus x squared is going to be positive, which means I have to take the negative root for sine omega t plus phi. So sine omega t plus phi is minus 1 over a square root a squared minus x squared. So substituting that here, I find that the relationship between dx and d phi is dx is square root a squared minus x squared d phi. So going back to the probability distribution, p of x dx is twice p of phi d phi, twice 1 over 2 pi. For d phi, I write dx over square root a squared minus x squared. So I find that my probability distribution function is 1 over pi, 1 square root a minus x squared inverse, or a squared minus x squared parentheses to the power minus 1 over 2.